two of us in this room who have benefited from his mentorship. And many of you who know the CMS at GCAL, he's one of the 3 or 4 original proponents of the GCAL, really saying that we should use silicon for calorimetry. And he has worked on that for a long time. Of course, before that, he was the project manager of the CMS ECAL. And of late, he has turned his focus on to really nail down timing to get more and more precise timing detector. So without further ado, I'll invite Professor Rusak. But before that, on behalf of the organizing committee of the positonium, the workshop on the positonium frontier, I invite Professor Mojumdar to give a small token of appreciation to Professor Rusak.
Oh, so how does that work? Can you hear me at the back? Okay. So, well, it's really a pleasure to be here. We've been now here in Mumbai for a couple of weeks now, and we're completely adapted and we're used to the traffic and everything else like that. So, okay, I'm going to give you a, no, I'm a physicist and I'm talking to the engineers here, so I'm somewhat intimidated by your expertise on this. But anyway, I'm going to give you a real discussion about, how we distribute clocks in different systems. In particular, I'm going to talk about modern systems towards the end of my talk. But I thought first I wanted to go through some bit of history of the problem of distributing clocks. So basically, as I said, I'll begin with a little bit of history. Then I'll talk about some general properties of digital clocks and introduce or explain to you a system which I've never worked on, but it's sort of always been there in the background of everything I've been doing on this timing stuff, which is the White Rabbit system, which is a system derived at CERN, which I'll talk about a bit then. How we do it in a different context of the CERN Large Hadron Collider, the CERN High-Luminosity LHC. And then finally, I'm going to talk about some work that we've been doing in the group to really nail down the business of how do you distribute a clock with high precision at low cost in a high radiation environment for a big detector where you have millions of channels. So everything we're going to talk about just wouldn't have happened without, say, Rohit there, who spent time here. You taught him well. He went to Bhubaneswar, NISA Bhubaneswar, where they also taught him well. He's been, without him, the work would not have happened. Plus, my electronics engineer, who did an awful lot of good work and was a genius guy, comes up with a good idea every other week. And some various undergraduates, the multiple undergraduates who come through our group who've made the measurements and been participating in the code development and things like that. So anyway, let me start with a little bit of history. Now, so it goes back a long way, as you all know, and if you start to look at, well, what is time and how do we measure it and stuff like that, the rabbit holes all over the place are everywhere. And I had to limit myself to just a few things. So I started with the idea of the railways. So the first inventor of the telegraph, they used the telegraph to align clocks in the 19th century. And there's a man called Pavel Schilling, who actually I'd never heard of before. He was the one who realized that you could have not just a simple current loop, but you have a long current loop and you can move a dial. And that way you could transmit a signal a long distance by changing current in that. And you can move a magnetic dial as the current flowed, which is what Ørsted discovered by accident in 1800, applied to the telegraph. In the UK, which is where it was first applied, Wheatstone, who you all know, I'm sure you all remember your Wheatstone bridges from your undergraduate days. He was quite an entrepreneur in this whole aspect and stuff. He has patents, men of the Royal Society. He was, in modern days, he would have been sued for plagiarism. However, he was the one who pushed the original idea of using the telegraph to communicate time to the railways, because it was going to be a problem. In England, in the UK, there's noon, which was defined normally locally by where the sun is in the maximum altitude. That was shifted by about 10 minutes or so within the UK. And this was a problem when it came to train timetables. And so the solution was to send by the telegraph a time signal to the line of clocks and so on. And the system was for 4 minutes before noon, the operator would tap once a second for 4 minutes, and then at noon he switched to twice per second, and that would give the exact noon. That was the initial signal they used to define this, but it got a bit more interesting after that. Anyway, consequence of doing this was we had in the UK Greenwich Mean Time. That was the meridian, which I don't know if you know the lovely story. Greenwich Mean Time was adopted universally in exchange for the UK adopting the metric system, and that was in 1896. They finally did it, sort of, in the UK in about 2010 or so. Right? Anyway, that led to, and the US was adopted in 1918, universal system. In India, things are a bit complicated. So 1870, it was noon was the official noon time for Indian Standard Time was defined over Chennai. And that was when the noon of IST was. And then it became standard in 1906. And then in 1955, Mumbai finally adopted. I don't know why there was this interval, but it's an interesting, I'm sure there's a life story about that, why that was the case. Anyway, so then became an interesting problem. So you can do this locally with your telegraph poles, but telegraph lines. But there was, of course, the undersea cables, which was, in fact, an amazing invention at the time. The fact you could send a signal from Australia to England or India to New York or wherever by an undersea cable, which was made possible by a wonderful material, gutta percha. I would recommend you look it up, because without that, they wouldn't have been there, and history would have been different. Anyway, I think also Wheatstone was involved also with the recognition that gutta percha was the solution to this. Anyway, because you of course have to take into account the velocity of the signal transmitting to and fro between the two things. So when you do alignment, and there were many patents on how to solve this problem. And many of those patents wound up in the Zurich patent office, where a young man named Albert Einstein was reviewing the patents. And he reviewed them because he was an expert on electricity and magnetism. And as we all know, in 1905, there was beyond seminar, I didn't quite know, a paper on special relativity, which came out of that. So I'd like to connect the special relativity, and we're going to come back to that, with the problem of aligning railways. So anyway, things changed, of course, with radio. Things got much better, much easier. And if you were in the UK and or you listened to the World Service, go back, I got it. Yeah, sorry, I can't quite get it. This was something which I grew up with. You may reckon, I don't know if you can hear that at the back, but it's Big Ben, and this is broadcast. And we all knew as a kids that exactly at the first chime, that was the real time. That was the precise time. Now wait how long it is between the pre-chimes to the end of it. It was still waiting for it. It's coming. And then there will be the 1 o'clock news or whatever, which will come after us. And this was how it was broadcast. I will stop there. You won't have listened to the 11 times I had on that recording. Anyway, so and radio was the source by which time was delivered, was broadcast basically universally. And personally, I was out in the middle of the Atlantic, finding my location using a sextant, and for that you have to have precise time. My watch at the time was not good enough to be reliable, and 1 second error or uncertainty corresponds to an uncertainty of 1 nautical mile when you're measuring your location. So I used to take the signal for the time from shortwave radio, which is broadcast on 3 different wavelengths, depending upon which time of day it was. Then along came GPS, and everything's changed from GPS. We use it all the time when we're stuck in traffic, or we're not stuck in traffic, and all that sort of stuff. It was a product of the Cold War. I mean, you probably know this. The major purpose, it was a problem it was solving at the time, was how do you locate a submarine that's about to send a ballistic missile? You need to know to calculate the trajectory where that submarine is, and they didn't want people rushing around with sextants looking, trying to figure out, doing sun sights and that sort of stuff. So the GPS was there. It was secret until 1983, when the Korean Airlines 007 was shot down over Soviet airspace because they'd strayed off course. After that, Ronald Reagan, who was then the president and the administration, made it public, put it in the public domain, so that to prevent things like that happening again. And it almost certainly was a navigational error on the part of the plane. First introduced by the military, version point of about a meter precision, and was downgraded for the rest of us to 100-meter precision. And then in 2000, they just took it off because there were so many possible interesting applications, which were commercial applications of it. So, and the time for GPS, which is used still in most systems as a for clocks, is the order of 10 to 14 nanoseconds in terms of the accuracies you can get. And then if you multiple repeated measurements, you can get down to about 500 picoseconds or so at the time. So whilst we're here, back to relativity, GPS, of course, as you probably know, has to take care, so since the height of the satellites is 20,000 kilometers. Am I right? Yes, 20,000 kilometers, which is about 4 times the radius of the Earth. And they're moving at about 4,000 meters per second. So that's a special relativity effect and a gravitational, so a general relativity effect. So the change in frequency for special relativity is 1 part in 10 to the minus 10, negative. General relativity is plus 5 times 10 to the minus 10 in terms of the changes in the frequency because of the gravitational or the velocity motion. And these lead to basically minus 8 microseconds per day due to special relativity, and 43 microseconds per day for general relativity effect. These, of course, add, and so one reduces the other, but it's not so simple because the orbits are not circular and so on and so on, and there are effects due to the ionosphere and so on, which have to be factored in. But basically, this was a real application, an engineering application of general relativity. And in fact, I know the engineers, when they first did this, they didn't put it in. They switched the correction off because they didn't believe it. But then when they saw the clocks wandering, they believed it. Okay, let's move on from history and anecdotes to the reference clock. What do we mean by a reference clock? So what are we actually doing when we send out a clock? Now, I'd say I use here a digital clock, which is sort of a sequence of up and down, zeros and ones, which have a regular pattern. And you want to distribute that same digital clock to a system which could be, 100 meters away. It could be 10 kilometers away. It could be 100 kilometers away. And you want to make sure that the phase difference between, say, a rising edge of one of those clocks is stable with respect to the rising edge of the clock that's over there. And if you have multiple systems, one is over there, you want it, and also that one over there, so you could compare the two in that way. So that's the problem you're trying to solve. There's the noise on this. So there are noise or fluctuations on this. The time difference changes. If it's a high frequency change, it's called jitter. So this is up in the kilohertz, megahertz type region. If there's a noise, that is called jitter. And there's another type of noise which is called wander, generally referred to as around 1 hertz, but in fact, wander can be at the order of like 10, sort of up in the kilohertz too, before you start getting into jitter. Jitter is actually nice. You can correct for it using a phase log loop, or PLL. I also use that frequently. A phase log, you can really clean it up, filter it out. You just by putting like a high pass filter on through, you can get rid of it. Wander, on the other hand, you can't. And so most of the work I'm going to talk about is how you correct for wander in a clock. So this is jitter. This is showing you basically the effect oscillations or variations at the edge of the clock. And then, we often refer to this in the frequency domain rather than the time domain, which is like up there. This is in the measurement in the frequency domain. There's actually a measurement, actually, you think you've made this plot. This is showing so this is the offset frequency, this plot you may see. This is showing the offset frequency for a digital clock. Central frequency, so and the vertical scale is in dB, decibels. So at one kilohertz off the central frequency, which could be like 160 megahertz, you have the probability is like here in this plot is 110, minus 110 dB. So it's a very small one. You come away to 1 megahertz away from 160 megahertz, you're down to the 150 dB. So you're really suppressing. So this is a measure that you can buy very fancy instruments for measuring this. You convert it back basically by doing a Fourier transform, and in order to determine what thing. This actual plot, I think we calculated that to be about 400 femtoseconds of noise by that formula. Sorry? Haha. That's around a megahertz. I have no idea what that is, to be quite honest. Anyway, oh, okay. So it's background noise, you're picking up on that. Wonder, again, this can be caused by such things as temperature changes to your fibers, which are connecting your sources. There are some nice pictures we have here. So this is the top picture. There's some measurements that we did a while ago. For a 25-meter cable of optical fiber inside a climate chamber, we roughly saw 3.96 picoseconds per degree Celsius. So you have a 100-meter long fiber, which is sort of typical in our high-energy physics experiments. If you have a 1 degree Celsius change in temperature, you're going to get something like 16 picosecond drift, a wonder, just from the temperature change. In addition to that, if your front-end electronics, your electronics is heating up, which it tends to, then you're going to get also a shift in the response of that, especially if you're using an FPGA, which tend to be very temperature sensitive. So about a factor of 4 more than your fiber optics. Anyway, so the point is, how do you deal with that? So again, in all applications, you tend to have a principal source, which is your source clock of some kind, which is conditioned by a atomic clock or conditioned by GPS or something else like the beam and the thing. And you're sending from the primary source to multiple sources. The secondary nodes, the source. So the trick is to basically you send the signal out, and then that source sends it back again. And then the primary source, you compare the phases of what comes back with what you're sending out, and you want to make sure that stays stable. That's the basic trick that this one's going to use. And you do it for both things, and you make an adjustment to the phase of the clock that you're sending out to ensure that stability. And this is basically the problem. So you're trying to do this in different ways for different types of systems. So how do you measure the phase to high precision? If you want to get to really picosecond type level precisions, how do you do that? So there is a wonderful circuit which we all use, White Rabbit, all the things we've been talking about. It's called the digital dual. Oh, I've done it again. Mixer time difference circuit. It's not. I always get it's mixer time difference circuit. And this actually is sort of coming back from FM radio. It's sort of basically inspired by the way FM radio works. So FM radio, you may remember, if you're old enough, FM radio where you have a carrier frequency or main central frequency, and then you modulate the frequency around that, and you beat the two against each other to derive the audio signal. In a sense, that's what we're doing here. We're just doing it digitally. So basically, so the way it works in this circuit is you take two separate clocks, which you're comparing with each other, you input them to the D input to a D-type flip-flop. So a flip-flop is where you can latch. What's on the D is transferred across to Q. This is a D-type flip-flop. Very standard. They've been around for many, many years. LS74, LS74, if you would remember from the days of thing. Now you then take one of the clock signals, put that to a PLL, and generate another clock, which is slightly offset with respect to the frequency to the other two. So these clocks are advancing in phase, and we'll eventually go for a full 2-pi swing and come back again. And you do that, and you take that offset clock, and you inject that, and you use that to latch the signals which are coming into the two D-type flip-flops. And you get something that looks like this. So it'll go through, and when the phases are aligned in a certain way, you're going to get the output of D will be low, and later on it'll switch back to high. And the effect of that is that you start off with this delta T here, which is small. It could be the order of a few picoseconds or so, and it gets amplified, makes much larger by using the beats of this. So this circuit is core to all the measurements I'm going to be talking about. So the second clock can have a frequency offset, which can be like, we in the lab, we use roughly 1 in 100,000ths away from the central frequency. It's really, really close. So that it really extends out the delta T to a much larger effect. Most people nowadays are using, like the White Rabbit system and so on, they're using basically an offset of 1 100,000th, sorry, 1 1/10,000th away from the central frequency. So that amplifies your 1 picosecond up to 10 nanoseconds or so. However, there's no magic here. These circuits have their limitations. And the real limitation for this is the time it takes for the time that's required for the signal at D to be stable before the clock edge comes. And this is called the setup time. Now, the setup time is for a FPGA is about 800 picoseconds. That's a very good for massive object with multiple gates and so on. You can buy, and this is the path we took, you can buy what we call RF flip-flops, which you can actually you can make them ring, so set, reset, with a frequency of about 12 gigahertz. So that tells you just how fast they are in terms of that ability. But this is a limitation for anything using an FPGA, because this is the generic devices and so on. We use, as I said, 100,000. So just to give you an idea what the frequency, we have an offset, which is from 160 megahertz clock, which is sort of 4 times the standard at CERN. We use 159.9984 megahertz as our offset clock. And that gives a factor of 100,000 in the amplification of delta T to the big delta T. So, okay, I wanted to go through that circuit because that's critical and central to the way we do things. So, what do we use it for? Okay, who needs precision timing? Turns out a lot of people do, right? Starting off with, of course, alignment of telescope arrays. Time stamping in the stock exchange. This is really important if that trade comes in before that one or whatever. This is used in the German Bourse system, I'm told. This is a GPS, not GPS. Large-scale experiments, we use this in our experiments. I'm going to talk about some applications we have in at the LHC. Quantum networks, where you want to get the coherence between the wave function in 2 different places, and you really want to have them aligned. The spec on that is about 5 femtoseconds. So it's a very, very tight alignment. Haven't got there yet, but we hope to be there soon. In nuclear and high energy physics, one of the big problems initially, this thing I've been mentioning, White Rabbit was basically developed for. You have an accelerated complex, you have multiple beams with RF systems which need to be thoroughly synchronized in order to be efficient transfer from one beam accelerator to another accelerator. And this is over a large complex. So we're talking about 10 kilometers from point to point. And these need to be properly aligned. The RF system need to be all lined up and so on. So there's this one telescope array. This is a picture from the Murchison radio. So this is the square kilometer array. in Australia. And these are the 4 large detector experiments which are going on at which are the LHC. All the ones which are, these are all sketches of them, they don't look like that. But to give you an idea, if you're not familiar with this is the sort of scale that of these experiments. This is the size of Atlas. And the problem you're trying to solve with this is you want to have at the far end of that detector, you want to have the clock aligned with the near end of that detector. And so you're separated by 25, 30 meters. And they're trying to align clocks separated by that much to sort of the order of a few picoseconds or so. And just to give you an idea, notice, did I count? Yes, oh, it's taking its time. There's a bloke here. I give you an idea of the scale of these devices. So this was sort of what's inspired our work in this area. So there is the upgrade to the LHC. One of the problems they're trying to solve with the Large Hadron Collider is within a 350 picosecond period is when the bunches collide and then move on. And in that time, you can get in the HLHC about 150 events occurring. And the idea was this is going to be really difficult to sort out, to find the signal, physics signal within that period. So in order to get rid of that background, things which have no interest at all apart from the event, which happens once, no more in your detector, but you can divide that 350 picoseconds into 10 35 picosecond slices. And you can say this event comes from that one, and all this stuff that's coming out of that time slot is of interest. Things which are coming out of the other times are not of interest, so I can ignore them, and they're not part of my analysis. So this is a space-time picture there showing how you can use this to get these slices. This is a classical measuring by time of flight a particle. So when the particle leaves, when it arrives at a particular detector. And then this is another one showing long-lived, so the range of long-lived particles which you might discover if you have good timing in the detector. So I've taken a slide from a talk which was given last week by Nicola Catilla. In the experiments at CERN, we're installing in CMS the MIP timing detector. I hate MIP. They call it that. I keep saying, no, it's not a MIP. Anyway, that's a war battle that's long lost. Anyway, at one end, they're using LYSO crystals, which are about 1.5 centimeters long, each read out with a SIPM at each end, because the propagation of time within the crystal is at 120 microns per picosecond. So if they're 1.5 centimeters long, you basically were adding, I forget, what is it, 100? So it's 1.2 millimeters. So you're adding about 100 picoseconds to those who have to know where they are inside the crystal. And that there are 330,000 channels of this in that detector. There's another one which we call low-gain avalanche diodes. So these they're called abbreviated to LGADs. These detectors are, so these are large area detectors, which are like where you have, instead of having a usual pin diode as we have with HG-Cal, which Rajdeep is working on, instead of that, there are pin diodes with a high electric field inside them, spread over a large area, so you get some avalanche gain through impact ionization inside the silicon. And they have a gain of about 20, and they are these large wheels of these things, and they have, what's the number? I couldn't remember the number. They are 3.5 million channels to that device, and all these are trying to measure the time to better than 30 picoseconds from minimizing such a vacuum on the sun. So these pictures shows where they're being installed on the detector. So they're being in the end caps and in the barrels. Anyway, but this is the problem. This is the detectors we're building. We were concerned initially that they would never achieve the 30 picoseconds precision because of the problem of the clock distribution. Anyway, we'll get on to that. So this is a description of a generic, how we solve this problem, generic timing detector. Rohit actually went through this yesterday in his talk, so you will have seen this before. But basically what you're doing is you have a detector, particle comes in, convert whatever you generate through your amplifier a signal, and then you input that into a time to digital converter and you derive a signal. The time to digital converter, or your ADC, has to have a reference clock which is working to, so that you can connect the signal, the time of the signal in the TDC with this channel with the same over there. So this is the basic problem. You distribute a clock to the TDC and you use the TDC, and you want to keep that alignment the same. And what you're doing is as your signal moves through above the threshold, you latch that information into the TDC. So when you come to these detectors, there are basically different sources of noise. There's a signal noise, which is fluctuations, Poisson statistics, amplification noise, and so on, or electronic noise, I have it there. That's coming from like dark current, shaping effects, thermal, and digitization, which is the precision of your TDC itself, and the reference clock, which you need to have, and that needs to be kept below, well below the goal of the detector. So I'm really going to talk, I'm going to continue talking about this part of the problem. These other three aspects are equally fascinating, but this one is what I'm going to talk about now. So let me talk about basically how that works, how it's done. So there's a basic link architecture. You've got a primary source, and you've got a secondary node, right? So you can condition that with an atomic clock, a cesium clock or a rubidium clock. These are now, they're getting small, and you can buy them, and they're not too expensive. Well, $4,000 is expensive, but they're not that expensive. They're not like they used to be 20 years ago. Or you can use GPS, and you can use what's called a GPS conditioned clock. And that can be a very stable clock, and that can be your master. Or in the case of the accelerator complexes, you can have the accelerator RF, and that's what you distribute to everybody, and everybody lines up to that. So you always have you have multiple nodes which you're servicing, and then beyond that, you then send that out to different detectors, and there you can have tertiary nodes, and so on. You can have a whole tree structure for distribution. The LHC, this is very much what we see, less so at, well, for the beams, they don't go through too many nodes. So there are two aspects to this, one of which is L, the distance from your primary source to your secondary nodes, and also intervals between the other ones, and also the number of nodes you're trying to serve. So I sort of roughly divide the world into two categories. One of which is where N is very large, like a high energy physics experiment, or L is small, so you're not far from the distance. And then, or the other one, like a radio telescope, beams stuff, where you have not that many nodes, maybe 100 or so, maybe 1,000, but not millions. L is about 1 kilometer. So this is sort of the two types of things. So here it is, White Rabbit, as promised. Okay, this is really designed for small n, small numbers of nodes, and large distances. It's a very nice system. It's based on commercial PCI Express and other similar cards. It actually, if you want to get a high precision node, you can buy them commercially. They cost about $40,000 a piece. So it's not something you'd ever consider for an experiment for multiple, but it's something if you have to do like 20 aligned, it's the right answer. The basic method, it uses a certain protocol where they actually add information into it about the clock. It was developed at CERN for beam control. It's now used in manufacturing, telescope synchronization, telecommunications, and as I said, time stamping in the stock exchange. And basically is that all the secondary nodes and the primary nodes, there's a free running oscillator on each of them, and you align those free running oscillators with each other. That's the basic concept of how you do it. So you have this exchange. So this is the primary master. This is the slave, primary and secondary. This sends a synchronization signal to the source. It then sends it back, and you measure T1 minus T4, and you measure, and you're told, you're sent back with this sent back, you're sent back to the oscillator, which is at this source. And they continue to exchange things until things are stabilized. It takes several seconds, maybe a minute or two, maybe 10 minutes for everything to settle down and to get to a very stable. And the typical is the order of 10 picoseconds. They say in their papers, if they really push it, they can get 2 to 3 picoseconds with this. Which is, and for many applications, that's sort of what you need. This is the case for the HLHC detectors and for other detectors, which will also make use of this. So where you have a large N, where N can be 1 million or so, and L with small could be about 100 meters. So the system there, you have the master clock, which is again driven by, in this case, driven by the machine RF, which is distributed to all the detectors and so on. So, and you want to distribute that clock to the smart, they use GP, and then it arrives at the counting room on the surface, and then it's sent through a cascade of FPGAs. In fact, there's 2 in this one, but in fact, it's about 4 levels. And at each time you send a clock which is encoded on a signal on a 2.56 gigabit per second signal. It's recovered by the FPGA, cleaned up with the PLL, and then retransmitted onto the next FPGA, down to the next FPGA. And so you have this sort of tree structure, and the red lines indicate the return signal coming back on the FPGA from the FPGA, which is sent on the same fiber, which is sent on the fiber that you use for reading out the data. So you have a fiber that goes down, which has the clock and control information on it, trigger information, so on. And then the data comes back up on a 10 gigabit per second thing, and you pull out the clock from these 2 and you align it. So this is, and that we have a precision of about 5 picoseconds. There are some issues with this in terms of resets, thermal stability of the FPGAs and so on, which limit it, but still, I think we're at spec. Pushing the limits, we wanted to go better than this, and the question was, how will we achieve that? So again, as I mentioned, using high-speed discrete components with several times the order of 30 picoseconds or so, we were able to get, with a system which we built using them, to get a system which gave roughly 100 femtoseconds precision in the phase measurement. This is a thing which we designed a long time ago, 4 or 5 years ago. I think there's one of these here, which is being used. And basically, the only difference, so this is the same DD-MTD circuit from before. This is what's called a deglitcher, which is how you manage the metastability, and then you actually extract the time difference from that. And in this case, we count clock cycles. Another component of this alignment is being able to change the phase of the signal. Now for that, we actually have 2 methods. I'm going to talk about one of them, which is the most interesting one, which is we built an ASIC which has a planar waveguide. So you have a waveguide which is on the surface of the ASIC, copper plates, copper lines between them, and you change the copper lines to change the speed at which you propagate through this waveguide. And these are done in cells of 61 cells inside this chip, and the signal will route itself around this pattern, and you can switch in or switch out. You can switch in the high or the low speed. And it is a planar signal that's propagating on the surface of the silicon coming out of the far end. This is really a very interesting device. It was actually inspired by the technology we use for beam steering on our cell phones, which has something like this, delay signals with respect to each other, but just on a larger scale. You have to worry about the impedance you change this here, you change the capacitance, you change the impedance. So we had to add capacitors in order to make sure you didn't lose any reflections. And this works at roughly 8 gigahertz and up to 8 gigahertz. And is incredibly stable. In fact, you could use it to measure the thermal expansion of silicon, right? Since it's almost a passive device. And we use that in a system using that phased DD-MTD system I showed you twice. One of which to generate the clock and to figure out what the frequency changes should be. We sent it down a 1 kilometer long fiber and stabilized it to 120 femtoseconds for a period of about 90 minutes or so. And then went out of the range of that particular device we were using. But for this time, it was very stable indeed. So this is, I started talking to our quantum people, I said, this is a great achievement. Nevertheless, we wanted to push it a little bit further. So again, detector system, small n, smaller. So how can you go below a picosecond? So we're getting to, with this system, which is impractical to use with those big things in a detector with discretes, you have to go to an ASIC. So there was this DDMTD ASIC designed by Rohit there, in order to make a flip-flop optimized for this application. So generally, a flip-flop has to be both short setup time and fast propagation time. And we didn't care about the propagation time, so one which has minimal setup time, we could design around that. And this was designed not in a IP block from TSMC, actually designed at the transistor level. And as you see there here, this shows the cadence estimation. So this is a simulation. So this is 1 picosecond, and the applied delay, and that up there is the measured delay. You externally apply delay to a thing, you see how and we expect to see a nice linear relationship there. So here was the ASIC, it came back, and Rohit that's Rohit's chip. We tested it in a system which was designed by Eric Fromm, our engineer, basically running at 730 megahertz, which is a magic frequency for these phase log loops. We could generate something which was 100, so 10 to the 1 in 100,000 offset frequency, goes into the ASIC. The ASIC has good classical devices, a Schmidt trigger. I don't know if you know what that is. It's something which which is used as trigger. And basically the readout electronics was I think a $3 or $4 TDC, because the signal's been extended and you can measure it precisely with a TDC to get back to where you were. And so that's what the system looked like. And this was like some of the early measurements we got with it. We were getting a precision of delta T, that's the phase difference between the signal, of the order of 76 femtoseconds for this, the precision of that. And then introducing a delay of 10 picoseconds, this is the linearity that we measure. As we shift the clock that comes into the DDMTD slightly by stepwise, and then we'll track it up with the DDMTD. It's a very nice. And then if you average your measurements over, I think it was 5 seconds or so, right? Then then plot 0 to 1 picosecond. You see again the nice linear plot, which was in the simulation. So this was and with the resolution that we can achieve with this is about 27 femtoseconds, achieving that. So it's really pushing the limit. So now essentially this is the problem of the clock distribution, we think. So next and final question, how on earth would you put that into an experiment, right? So this is a schema that we came up with. Basically, again, how does it in an experiment? I need to explain this a bit better. So, yeah. So this is on a detector, we talk about the front electronics, which is sitting on the detector itself. So that can be coupled to a crystal, that can be coupled to whatever, and is separated by an up-down link, which can be 100 meters of optical fiber, for example. And you're going to have one of these boards which will talk to some detector components. And there'll be another one talking to another set of detector components, and these will send their signal, receive the signals down, the clock will come down, and will send the data back up again. So this is the basic structure of all the systems we have in these big detectors. So so this is normally front-end readout. This has an ADC, talks to the actual devices, the preamplifies it here, amplifies the signal and propagates it, serializes and shifts it up. So we want to add to this, which is on the front-end board of this DDMTD phase detector. And then you would have that here, and then you would have a delay, which you can use, that remote delay which we had, which would also be part of each of the front-end boards on the whole detector. So there is one issue here, which is you have to have an offset clock, which comes from somewhere. So our concept is that we bring down from exterior a single shared offset clock that's shared between a subset of the detector, so maybe 1,000 channels. 1,000 of these versions, they would all receive the same offset clock, and with this, you'd measure the change of fluctuations of the wander due to the signal coming down from the outside, and you'd be able to correct for it on here, so you maintain the stability. For high-energy physics, for HEP, for LHC, this needs to be radiation tolerant, which we haven't yet proven, but we expect it will be, because the transistors are straightforward. It's all using standard TSMC 65 nanometer processes. And basically this would have, and this little phase detector in here would consider the flip-flop, a deglitcher, a counter, which would go to an edge detector, and then that would be used to measure the difference between this shared offset clock that was coming in from outside, and this clock was coming down from the exterior reading. If those two start to change, then things are wandering and you can bring it back again. So this is a schema that we've worked out. We've yet to actually, do it but we think that we do it in an experiment yet. But we think this schema, by having this detection system on the detector itself, you can really align things very, very precisely. So anyway, basically, the point here is that this part of the problem we think is solved, or at least in a very good position now for future very high precision experiments. And we know how to do that. Now we have to figure out the other parts, like the signal and the electronics and so on, in order to optimize precision timing. And that's the end of my talk. Thank you.
Another question.
So now that you have a system to measure time differences very precisely, so other than clock distribution, can this be used for some fundamental physics measurements?
Of course. I mean, once you get to be able to measure things to this type of precision, other things pop up as possibilities. One of the things we started just since you're basically using this to measure, for example, the index of refraction of a material. So you have two light beams which go through, one which goes directly and one which goes through the material. You compare the phase changes and you remove the material and you can see how the difference is, and that will give you index of velocity of light through the material. That would be one way, and you're measuring it to this high level of high precision. There are other ones. LiDAR is another possibility. Many other aspects of this. So this is like, the trouble is, we're not engineers, we're physicists, and we're not businessmen.
But let's say for these fifth force-like measurements, fifth force or stuff like that, for that, to get to the limit, what's the kind of delta T's you need to get to?
I've been told that this is sort of like either in the domain where this is of interest, or we're really close to it. And I should say, this was done at room temperature. These measurements were done at room temperature. They were not temperature stabilized, and we didn't cool down to -40 or temperatures to really minimize the noise. So there is improvements which can be made, which are not practical in an experiment, but in that type of measurement certainly could be. Yeah.
It was not clear how you are changing the delays using the waveguide.
How do I implement the delay?
Yeah, using the waveguides.
Sure. No, I covered that. This was in this. This is how this was done with this circuit here. So this circuit here is a digitally delayed, what was it? DCPS, digitally controlled phase shifter. So you apply an I2C signal to it, and you select for each of the cells which one you want to have as a low delay, fast or slow, low delay, small delay, delay or small delay. And you can select, by selecting the cells, you can adjust the time that it takes for the signal to propagate from the bottom left up to the outside. And we can do that in steps of 30 picoseconds. Sorry, 300 femtosecond steps. And with the dynamic range of the precision steps of 20 picoseconds. And then on top of that, not shown here, but in another version, we actually have lump delays, which allow us to extend the range up to 250 picoseconds. And this is again made in TSMC 65 nanometer process.
So in the clock distribution network, so the clock is being transmitted through optical fibers.
The clock is being transmitted from where?
Optical fibers.
Yes, that's the usual way.
Yeah, so but when in FPGA or PLL or flip-flop, it is electrical signal. So somewhere you have to convert the optical signals to electrical signals. So
Yes.
like what is the timing of that? Like does that timing matter, the conversion times?
Generally not. It's stable, but it is temperature dependent. Again, it's part of the wonder which you would get in the fiber and in the electronics, and that's one of the places where you can introduce wonder by changing temperatures and so on. We actually, one of the plots I showed was if you took, where is it? VTRX. I think, did I put it here? Yes, this plot here. This one, this is minus 30 plus 60, 0, 200 femtoseconds, 200 picoseconds. And that was just taking optical receiver, LPGBT, if you know what, that's one of the circuits we use, and putting that in an oven and changing the temperature. The fiber was outside when we did this. And you see it's basically 2 picoseconds per degree Celsius. So again, there's stability and stability on that. And, you know, as we all know, electronics heats up, it gets stable, but it takes a while to get there, which is the typical problem.
But it's like just like a constant, it is not variable.
Sorry?
It is like a constant time delay. It's not like variable time delay.
No, it should be, but it is temperature dependent. So if the temperature is constant, it will be stable. If the temperature is changing by small amounts, it will not be stable. So but these effects actually add together. So you have the effect of the fiber, you have the effect of the thing, the effect of the FPGAs, which you have in your electronics upstairs, and so on. So it's tough. It's really, light travels 300 microns in picoseconds. There are a lot of effects which come in at that level, which you really have to worry about to get this type of precision.
So the kind of wandering you want to calibrate and taken out, can we do pulsar timing as an input to do that?
Pulsar timing?
Yeah, millisecond pulsar timing. It's a long-term wandering, but that has been tried, in atomic clocks. But
Yeah, no,
so this is possible in your.
I don't know. I'm not an expert in anywhere on pulsar. I've talked to the pulsar people. These people who do nanohertz for gravity waves and the pulsar timing.
So we actually have a copy of this system in TIFR, and I forget the GMRT people did express interest, the pulsar timing array guys, to see to what extent they could use it. We still haven't taken the system there, but yeah, exactly the pulsar timing array folks in GMRT contacted.
Well, I'm sure we'd be very happy to share the ASIC, which is probably about a factor of 5 better than the system which we have here. It's custom designed ASIC for this application. Sorry? Okay.
Any of the online audience has any question, you can unmute. United States. So
Okay.
he's joined me again. Thank you so much for coming.
Thank you very much.
Please join for the discussion.
I'll drop Zoom.